Okay, so we're going to spend today doing some review on chapters 10, 11, and the very, very beginning of 12. And the test is Monday. So we'll start with 10.1. So there is a question on 10.1 on the test. So 10.1 is the design study vocab, elements of a design study. What are the response variables, dependent variables? What are the factors? What are the factor levels? What are experimental units? What are treatments? Okay, all of that kind of stuff. So it's a multiple choice question on the test. What are the whatever? So it goes through the description of the study and then asks you what are whatever the vocab is, and you have to pull that out of that description of the study. Okay, so there is one of those on there. So read through 10.1 again, refresh your memory on the vocabulary. Okay, if you want to write some of those definitions down on a cheat sheet, you're welcome to do that. So you still do get an 8.5 by 11 piece of paper for this. So take advantage of that. All right. Complete an ANOVA table. So I will give you a piece. I'll give you the ANOVA table. It's mostly blank. Okay. I'll give you two of the numbers here under sums of squares. I'm not going to guarantee which two. In this case, I gave you sums of squares for columns and sums of squares for total. The sums of squares total. And you have to fill in the entire rest of the table from that. Okay? So, and from the description of what's going on here. So, how do we find the other sums of squares here? So in this case, how do we find sums of squares for errors? So you got to understand the relationship between these three numbers, right? So this one plus this one has to equal this one. So to find the missing one here, we're just going to subtract. All right? 1246.2286 minus 318.50914. So 927.71946. Okay? So there's sums of squares for error. All right, we need to be able to tackle degrees of freedom here. So how do you find the degrees of freedom? So you need to know your sample size. Okay, so this was our honey, dextromethorphan, and a control group study on cough suppression to see whether or not dextromethorphan or honey worked better than nothing at all. So we had 35, 33, and 37 in there, which I believe is 105. Right? Yeah, 105. 105, yeah. So my sample size and the total N is 105. So how do I divide up the degrees of freedom for this? So what's the degrees of freedom for treatment? In this case, what's called columns. What's the degrees of freedom for treatment? 2. Why? Treatment group, right. It's one less than the number of treatments. I got 3 treatments here. Honey, dextromethorphan, and control. So degrees of freedom for treatments is 2. What's the degrees of freedom for error then? So degrees of freedom for treatment is equal to K. Okay, where K is your number of treatment groups. And what's your degrees of freedom for error? N minus K. Very good. This was K minus 1. There we go. Degrees of freedom for treatment is K minus 1. Number of treatment groups minus 1. And degrees of freedom for error is N minus K. So we had 105 kids in this study, and we got 3 treatment groups. So 105 minus 3 is 102. Okay? and the total there should be 104, which should end up being one less than the sample size. Okay, so one less than 105. Okay, all right, now we got to do mean squares. How do we do mean squares? I'm going to have to shorten this up, aren't I? Here we go. Let's do this. 927.71946. There we go. Okay. So we fill that in. All right, now how do we do the mean squares for columns? Good. Sums of squares divided by degrees of freedom. So 318.50914 divided by 2 is 159.25457. How do I calculate the mean square for error? Same thing. We're going to take the mean square or sums of squares for error, 927.71946 divided by 102. So this one was 9.095288824. Okay? All right. So there's mean. How do I do mean square for total? You don't. Okay? Nothing goes in that block. Okay. Now that I got mean square for columns or treatments, that's the 159, and mean square for error is the 9.1. How do I calculate the F statistic? Pick up my marker. There we go. How do I calculate the F statistic? Divide. Right? There we go. So we're going to take the 159.25457, 159.25457, and we're going to divide by 9.095288824. And I got 17.50956671. Okay. And if needed, I also need to be able to calculate the p-value then. Right? How do you calculate the p-value for that particular F statistic? What do you need? FCDF on the calculator. Very good. Let's see how the calculator's deader than a wedge this morning. All right. All right, let's reboot that. All right, so yeah, we're going to go to distributions menu. We're going to go to FCDF. Okay, and what are my arguments for FCDF? What do I have to put in there?
And then it's a large collection of nines.
Yes.
Then your degrees of freedom numerator followed by degrees of freedom for the denominator.
Perfect. Okay, so remember the F distribution is some distribution that looks like this, skewed right. The shape of it, what the numbers are here on the x-axis, depends on your numerator and denominator degrees of freedom. Okay, so it's really, really hard to tell from the number 17, right? 17.509, how far out that is. I don't know if it's here, I don't know if it's here, I don't know if it's here, unless you have some sense of what the degrees of freedom are for every different F distribution, okay? So I got 17.509, and I want to know what the area is above that. That's my p-value. So I need to calculate the area above that, and I can do that with the FCDF. So I'm going from 17.509 17.5. I'm going to round it off to 17.51. That's close enough. 17.51 to, now the upper end, when we were doing z-scores, we used 99, because that was a long ways up in terms of standard deviations, but I don't know how far up 99 is with this, so this is where we put in a bunch of 9s. That should be sufficient. You also needed the numerator and denominator degrees of freedom, right, from your ANOVA table. So the numerator degrees of freedom was 2. Denominator degrees of freedom was 102. So we'll put in 2, 102, okay, and calculate that. So, all right, 2.9 times 10 to the negative 7th. So that's pretty small. So we were actually a long ways out there, right? So 17.509 is probably not here. It's probably like way out here, right? So there isn't much out here above 17.509. Okay? Okay, so it came up with a low p-value. So what would that mean? What do I do with that low p-value? What would be the result of this test? We're rejecting. What are we rejecting? We didn't really talk about hypotheses. What are the hypotheses for an ANOVA test? Good. The null hypothesis is that all the means are equal. In other words, that there's no difference between any of the groups. In other words, whatever you're doing to the groups isn't making any difference. Okay? That's your null hypothesis. Your alternative hypothesis is at least two means differ from each other. Okay? So in this case, with that result, with that really low p-value, we're going to reject the null hypothesis in favor of the alternative hypothesis. So at least one of these groups is different than the others. Okay? So we haven't dug into yet which one is different or in which direction it's different, but I do know that at least one of them is different. So either giving your kids honey, dextromethorphan, or nothing has a different result, okay, than one of the other groups. All right? So that's the F statistic, an ANOVA table. So you need to be able to complete an ANOVA table all the way through to finding an F statistic and a p-value. Okay? So what was my 2.9 times 10 to the negative 7th? Okay? So that's that part. Complete an ANOVA table. Find the p-value for an F and interpret it. Very good. We've covered that. All right. So from regression outputs, so next we're going to talk a little bit about linear regression. Okay? And let me remember what I was going to do for this. So given the sums of squares for error on a regression, find the standard deviation. So when I do a linear regression output, let's just do a linear regression thing from beginning to end here. We'll do that, and we'll talk about how to dig some of that stuff out of the table. Okay? And the first thing I want to talk about with linear regression is how do you pick what is going to be the dependent and what's going to be the independent variable. Okay? So sometimes you got to read through the text a little bit and look for some hints. Look for some key sentences that give you an idea of which one's supposed to be X, which one's supposed to be Y. Because sometimes it isn't real obvious. Okay? So a handheld digital camera was used to photograph the moon's orbit, and the pictures used to measure the angular size in pixels. So basically, how big is the moon? Okay. At various distances, heights above the horizon. Okay. The photographer wanted to predict the moon's size based on the moon's distance above the horizon. There's your sentence right there. I don't know if I can write on this or not. What's he trying to predict? He's trying to predict size, right? So that means size is the what? X or Y? Y. Okay, so sometimes it helps me when I'm doing these things, I'll actually go through and do this, right? So Y is the size and X is going to be the height above the horizon. I believe he's measuring that in degrees, right? So in this study, identify the dependent and independent variables, right? So if we're predicting size, that's my dependent variable. And my independent variable is height. Okay? So that's what you need to be able to look through and read through, see if you can find something about you're going to make a prediction of this based on that. If they literally say one might be dependent on the other, okay, we think child mortality rate might be dependent on the number of TVs per household. Whatever. Okay, look for some kind of sentence like that that talks about how they're trying to think about the relationship. Okay. And then you got to set up your X and Y according to that. All right? So here's our data for this study. Okay? So the angle in pixels. Okay? So they're taking a picture of the moon with a digital camera at various heights and using that digital image and measuring how tall the moon is in pixels. Okay? And correlating it with this. All right, so when I go to do a linear regression, I figured out which one's supposed to be my dependent and independent variables. What do I need to do next? What do we always do first for scatter plot before we start grinding anything? We have to look at a scatter plot. So scatter plot, what's my X variable? My X variable was height. My Y variable is angle. So you'll notice this one's in here backwards, right? Okay? Don't read anything into the order in which your data is given to you. You have to read the problem and decide which one's X and Y on your own. Okay? All right. There's our scatter plot. Seems reasonable. The shape seems linear. I don't see any really obnoxious outliers. So I think we're good to go there. All right? All right, so we'll throw that back. And now I can do stat, do a regression, simple linear. My X variable is height. My Y variable is angle or size. Okay? And I'm not making any predictions yet. Okay? All right, so what kinds of things do we need to be able to do here? So, let me do this. Let's just look at the bottom of this without giving away any of the goodies on the top. So if I only gave you this much of the table, which is kind of what's going to happen on the test, is I'm not going to give you all the goodies. I'm going to see if you can pull out some of the goodies, okay, from this stuff, okay? So first of all, what's my regression equation? I'm not even going to say y. I'm going to say angle in pixels, right? equals what? The numbers are there. What's the model I'm trying to fit? Y hat equals beta 0 plus beta 1 x1. What's beta 0? Boy, I'm glad we did this today. What's beta 0? Look at the form of the equation. What is this? It's the y-intercept. Yeah, 320.6, about 320.6 plus, yeah, that number, 0.0834 times height, right? And I think that's in degrees. They're measuring the height in degrees, which annoys me a little as a math teacher, but I think that's what it is. Okay? Okay, so there's the regression equation. So it's these numbers. When you talk about the parameters here, that's these numbers. Okay? So intercept, slope. Okay? So in simple linear, you only got one beta parameter. You only got one slope parameter. Okay? And that's this one. And there's your y-intercept parameter. Okay? What are the units? Can you explain to me what this means? What's that number mean? 0.0834 what? What does that mean?
For every increase in an angle or increase in height, there's going to be a 0.08 increase in the angle.
Right. The units on this is 0.0834 pixels per 1 unit of height, whatever that is. I still think it's degrees from what I remember reading in this problem. But okay, so I expect, and since it's positive, right, we're going to expect that the number of pixels is going to go up by this much for every 1 unit of height. Okay, so you need to be able to pull one of these out and explain what it means. Okay, there is one of those on the test. Okay, and that's interpret the meaning of beta I. That was this one. Okay, I can't remember if it's a simple linear or a multiple regression, but it doesn't matter. It's always the same, right? So the units on your slope are always, the slope is rise over run, right? Rise is the y-coordinate. So it's always the units of this on the numerator per 1 unit of whatever this is. Okay? That's slope. It's always rise over run. Okay? We'll look at another one here on a multiple regression, I hope. Okay? All right. So there's my regression equation. Okay? What's the standard deviation of the error of measurement on this? Okay? So there's actually a question on the problem. If I give you a sums of squares for error, if I give you this number, 3.56, if I give you the sums of squares for error, you should be able to get to what is the variance in the standard deviation of my errors. Okay? How do we do that? What do I do? What do I need to do with sums of squares for error? The degrees of freedom for error, right? And the degrees of freedom for error, when you're doing linear regression is equal to n minus the number of beta parameters. So this one was k plus 1, where k is my number of beta parameters. In this case, since this is a simple linear regression, this is 1. There's only really one slope term, right? This one is for the y-intercept. So there's your degree of freedom for the y-intercept. This is how many slope terms we got. Okay? So this one's going to be, there were 13 data values here. So a 13 minus 2 is 11. So the degrees of freedom for this one is 11. So we're going to take your sums of squares for error and divide by the degrees of freedom for error. That gives you the mean square for error, which for this problem I'm not going to give you directly, but we happen to have it on the table here. Okay, so that's 0.324 is equal to mean square for error. Now the mean square for error is the variance of your errors. So now how do I find S? I guess I should have said S squared. I'm using them more or less interchangeably here because we're assuming they're equal. Okay? That's S squared. So how do I find S? Square root it. Okay? So the square root of 0.324 is about 0.569. So S is approximately 0.569. Okay? What does that mean? How do I interpret that? Remember what the big takeaway was from my day with my advisor? This is my predicted value. I expect my errors to cluster around this line. They're not going to be exactly on the line. I expect them to cluster around this line. I expect them to be normally distributed. Okay? And the standard deviation of this normal curve is 0.569. So when I say interpret that, usually what I'm fishing for is that about 95% of the values for that particular value of x, for whatever this x is, okay, about 95% of the values will fall within 2 standard deviations of the predicted value. So that's 2 of these up and 2 of these down. Okay? So if I double this, times 2, about 1.14. We'll call it 1.14. Close enough. Okay? So an interpretation of that would be, I would expect about 95% of data values to fall within 1.14 pixels of the predicted value. Right? 1.14 up, 1.14 down. Okay? I'll make this a little more practical for you. This was the linear regression I did for Aspire scores versus pre-ACT scores, remember? There's my estimate error of standard deviation is about 2.67. What does that mean? That means I'm going to expect about 95% of the predicted of the pre-ACT scores to fall within, was double that, 5.4, right? Almost 5.4. Within 5.4 points, one direction or the other. So my prediction interval, my confidence interval for predictions is over 10 units wide, right? This is the kind of thing this is one of the things you look at to see how good your model is working, okay? How good of a prediction are you going to get, okay? It's like, great, yeah, I can fit a line to this. I can draw myself a line. There's my prediction line. And for any given x value, I can make a prediction. I predict the y is going to be that. Well, that's handy. But how good is that prediction going to be? Where is your data? Is your data like right here? I mean, if your scatter plot looks like this, I think your prediction is going to be pretty good. If your scatter plot looks like this, that might be the best fit line, okay? But I don't think your prediction is going to be as good. That make sense? Okay? So that's what this number is telling you, okay? It's giving you some idea of how wide is this going to be. And the width of your scatter plot is more or less 4 of these, right? 2 up, 2 down. Okay, that's a 95% confidence interval. 95% confidence interval is more or less 4 standard deviations wide. Okay? Okay, how am I doing? I still got 15 minutes left. I can get through some more stuff. All right, what are we talking about? Linear regression output. All right, so interpret the linear regression top to bottom. So we're still talking about this. This becomes more important with the multiple regressions, right? So when you do a linear regression on software, you get an ANOVA table. If you got sums of squares and mean squares, you can use that to find this stuff. That's great. The F statistic is more for the multiple regression. Oh, let's talk about some stuff up here. How do you do, what is the rest of this stuff? What's a t-stat? Why do I have a t-stat for slope? What the heck is that about? Do I have a hypothesis test that goes with that? What's the hypothesis test for that particular line of stuff? Null hypothesis. So, pardon? No, it's not an interaction. That it's 0, right? So the null hypotheses for all of these over here and the p-values and stuff are all for this hypothesis test, is that beta I could be equal to 0 versus beta sub I does not equal 0. We generally ignore the intercept one. I don't even know why they put it on there. Okay, most of the time I don't really care if the y-intercept is 0. But in this case, let's talk about beta 1. Your slope. Is it okay for your slope to be 0? What does it mean if your slope is 0? There's no correlation. X is changing and y is not. So changing x doesn't seem to be having effect, right? So if your slope is 0, that would be bad. It tells you that there's no relationship between your numbers, okay? So if you want a significant finding, you want to be pretty sure that your slope is not 0, okay? So that's the test that you're seeing here. How do they calculate this test statistic? T. The T for any particular beta is equal to the beta value, the particular beta that you got, divided by the standard error for that beta. And the standard error is always on your output here. So here's the estimate, here's your standard error. Okay? So for this test, for this t statistic, you're doing this number, 0.0833, divided by this one, 0.008867, whatever. And you get 9.4. Well, I don't care how small your degrees of freedom is, 9.4 is a fair ways up there. Right? 9.4 standard error is above the mean. Okay? This is the p-value associated with that. This is the probability that it could actually be 0. Right? So that's fairly small. So we're going to reject the null hypothesis in favor of the alternative hypothesis and say, I'm pretty sure the slope is not 0. Okay? So that was a significant result there. You need to be able to calculate this and this on your own. Right? Let's talk about degrees of freedom for a second. Degrees of freedom is 11. There were 13 data values. You see how we got degrees of freedom again? So the it's not the standard error so much. It's just the p-value. That's what it is. So the p-value is based on degrees of freedom equals n minus 2 in this case. Once again, it's the number of beta parameters that you're looking for, right? We got 2 betas here, including the intercept, so, right? So in this case, it's n minus 2. So you should be able to calculate this and the p-value. So how do you get from here to the p-value? I'm sort of glossing over that. How do you get a p-value from 9.4? Remember TCDF? Right? We're going from 9.4 to 99, and on this one you have to put in the degrees of freedom as well. So we'll say 11 degrees of freedom. Okay? So that's where you get the p-value for the t statistic. All right? This is going through this test and looking at the questions and thinking, just having graded it once or twice before, this test is one of those reading tests. You need to read problems carefully. Okay? And there's some easy stuff to miss. And there's some stuff that a lot of students have missed before. All right, what have we talked about? We've done the design study vocab. We've completed an ANOVA table. Find a p-value for f and interpret. Given a regression, find the sums of squares, find the variance in the standard deviation. Complete a linear regression top to bottom. Oh, we didn't talk about r squared. Let's do that real quick. So what's the r? How do you interpret an r squared for this? How do you interpret an r? So in this case, r is 0.943. What does that mean? Good. Strong positive correlation between x and y in this case. Okay. What the r squared for this is 0.89. What does that mean?
The regression model accounts for about 88.9% of the variance.
Right. Okay. About 88.9% of the variance in angle is accounted for by changes in the height. Okay? Good. So you need to be able to write a sentence like that from r and r squared. Okay? All right. Got that. Find and interpret the standard deviation for regression. We talked about that. Locate and interpret r and r squared. We just hit that. Find and interpret a t-score for any particular beta. We talked about that, right? So here's the t-scores for your betas. We probably don't care so much about the y-intercept one, but there's the t-score for the slope for this one. So we're pretty sure that's not 0. Okay? And that's what's important there. Interpret the meaning. Okay, so interpret the meaning of beta 1. So we'll look at another slope example here real quick and see if I can find StatCrunch. Where's my plot the following lines. My kingdom for a data set. Where's a data set? Okay, consider the following. Let's see. This is just random. Measuring the moon's orbits. Flood typing. Here we go. Flood typing. So what are we doing here? Refer to the analytical chemistry study in which medical researchers tested a new method of typing blood using low-cost paper. The researchers applied blood drops to the paper and recorded the rate of absorption, called blood wicking. The table gives the wicking lengths in millimeters for 6 blood drops at each of a different antibody concentration. Let Y equal wicking length and X equal the antibody concentration. Okay, so Y is wicking length. In millimeters, and X is the concentration, and they're not apparently going to give me that. It's, probably moles per liter or something like that, stupid like that. So concentration. So we'll say whatever that is. All right. So I got data for that. Maybe blood type. There we go. StatCrunch. Here's my StatCrunch data. All right. So look at a scatter plot. My X variable is concentration. Y variable is wicking length. Ooh. Sketchy. I got issues with this one. First of all, if you include this data value, it looks like it curves. You could think of this as an outlier. Because if you throw this point out, you have a fairly decent linear regression here. Okay? But beside the point. Okay? All right, so I would be reluctant to do this process. But what I want to get to, I want to look at the units of slope again. So I come up with this output, and my estimate for slope is -8. Beta 1 is -8.04. -8.04 what? What does that mean? Millimeters per 1 unit of concentration, whatever that is. Can you interpret that realistically? What am I saying here? What's the fact that it's negative mean?
For every unit of concentration, you're going to go down 8.04 millimeters.
Right. For every time I increase the unit of AB concentration by 1 unit, I'm going to expect 8 millimeters less of wicking length. Okay? I'm going to expect it to wick 8 millimeters less. Okay? So you need to be able to pull this number off of here and then tell me what it means in a sentence. Okay? So that. So on a printout of a multiple regression, you should be able to find the regression equation. Multiple comparisons and means. And tell me what those slopes mean too. Okay. Here's the grandfather clock one in case you've forgotten. This is the output from the grandfather clock. What's the regression equation? We're trying to predict price equals, blurt it out, we only got a minute left. What's the y-intercept? Negative 1339, right. Negative 1339. And then I got two slopes. 12.7406. We'll call it just 12.74 times age. And then I got an 85.953. So plus 85.953 times number of bidders times num bid. Right? So there's the regression equation for that. Okay? You should be able to pull out the r squared, find the sums of squares for error, and calculate the variance from this, which is exactly the same as it was for simple linear regressions. Okay? You're going to find your sums of squares for error, divide by the degrees of freedom to get the mean square for error. This is your variance. You take the square root of this, that's your standard deviation. Okay?